organizers who invited me to give these lectures. And I also want to thank Michael Hopkins for giving an introduction that is also applicable to my lectures. Actually, Mike gave me too much credit for the conjectures. Some 10 years ago or so, I did conjecture something. And the first conjecture is that there are some omega spectrum, B and F. B stands for bosons and F stands for fermions. This describes some states of bosonic or spin Hamiltonians on the one hand and fermionic Hamiltonians on the other hand. And of course, these are omega spectra, and same is true for F. And one can interpret this Bn as some construction B on a sphere relative to a point, and B0 for high N may be complicated, but there is another spectrum, Fn, that corresponds to fermionic systems, and F0 is Cp infinity pro Z2. And I still stand by these conjectures. And I also guessed with the help of Mike and Dan Fried, who taught me about Anderson duality, that Bn should be maps from MSO to Iz, the Anderson dual of the sphere spectrum should be by units. And you may notice that the second homotopy group of this is Z. That's why the shift is necessary. And similarly, spin. But I haven't made much progress on these conjectures. And actually, I've grown doubtful about those.
Alexei, I have questions here. Alexei?
Question. Oh.
Question from the bomb side.
Okay.
Where is N on the right-hand side? On the left, you have N. On the right-hand side, you have no N.
On the right,
N on the left, and then there's no N on the right.
E and F. So that's spectra. Yeah, thank you.
But what is the Bn? There's a Bsn point. What that means?
Some construction. It's basically the space of spin Hamiltonians on a sphere relative to its boundary. The boundary is collapsed to a point, and we actually ignore anything that happens around that point.
Maybe I see it roughly is a space of a Hamiltonian with no boundary.
Yeah. Well, no, I wouldn't say that. The boundary is necessary because basically we're talking about Hamiltonians on a plane.
Okay.
And those Hamiltonians, if we truncate them to a ball, may no longer be gapped. They will be gapless on the boundary. So we have to ignore the boundary. And that's why we do some relative construction. On the next lecture, I'll describe how to do relative constructions. So now, Mike and Dan made actual progress on this kind of calculations because they assumed that this Hamiltonians or whatever objects they are have Lorentz symmetry and reflection positivity. These are very strong assumptions. I don't know how to derive that from the Hamiltonian perspective. And right now, when trying to approach this question, let me describe how things are supposed to work in general. It's just a natural progression. We start with concrete objects like states, or quantum states, which are ground states of gapped Hamiltonians. And impose some conditions on those states, like invertibility. On the next lecture, I'll define invertibility. And then we're supposed to get an abstract omega spectrum. And then we're supposed to calculate this spectrum. It will be a concrete spectrum. First step, non-trivial, but it doesn't require much knowledge about Hamiltonians. We need to turn some discrete objects like collections of points and things like that into continuous objects and introduce relevant topology and things like that. And one can indeed get an omega spectrum, but the next step is difficult because here we need actual understanding of Hamiltonians or gap states. We need analysis. And I'm convinced that there is no easy way to solve this problem. So we decided to start from basics and just build some tools and hope that at some point it will click. By we, I mean Daniel Renard, Milo Moses, Isaac Kim, and myself were studying gapped Hamiltonians and in particular topological Hamiltonians. We have definitions of a bulk energy gap that allow gapless modes at the boundary and topological systems. And these are just basic definitions, and we're showing some properties, and hopefully we can prove or disprove Lorentz symmetry and reflection positivity later. And since I'm now convinced that this is the most important thing, analysis is important, I was going to give lectures about some definitions. Of course, these are basic definitions. What a gapped, how does one define a gapped system that is gapless on the boundary and things like that. But the organizer said it would be too advanced. so I'm now focusing on this step. And I'll mention the second step on the next, on the last lecture. And this step will be illustrated by free fermions. Free fermions are nice because the tensor product structure comes direct product, which is much easier to deal with. And the answer for free fermions is no. the concrete spectrum will be the spectrum of KO theory. Of course, it's just a roundabout way of doing KO theory. There are better tools to do that, but hopefully the tools I will introduce are equally applicable to invertible interacting systems. Okay.
Is that one the generation from free fermion to inverting fermion? That's all inverting all the time. That's straightforward, or there's some quite not
It's not straightforward. It requires some analysis. It requires definitions that have certain properties. And the important properties I want to describe later are locality and softness. So local and soft. This is my main slogan. And local means that all properties should be defined locally. We never have to think about an infinite system and even a very large system, because an information about a quantum phase is contained in a small piece of that phase. And soft means that our definition should allow more or less arbitrary but small deformations. And once the definitions are constructed, then this step should be relatively easy for invertible systems. And actually, there is a recent paper by Kubota who claims to have solved this problem, and he constructed an omega spectrum. I don't understand his solutions. I'll tell you about my proposed solution, which is incomplete at this point. But so much for the introduction. In this lecture, I want to give you some feel of related physics, because we have to start with a real world object and then made some abstract theory. And then I'll introduce the formalism of free fermions. So a concrete system I want to discuss is the transverse field Ising model, which is related to a Majorana chain, and a Majorana chain is a free fermionic system, whereas the transverse field Ising model is a spin system. So transverse field Ising model is a Hamiltonian of a spin chain, and there will be spins numbered from 1 through n. Each spin is a copy of C2, two-dimensional Hilbert space, and I'll use Pauli matrices to describe operators acting in this space. So let me just remind you, sigma axis and sigma z and if we want to apply any of these matrices to a particular spin, we use this notation. Sigma z sub L.
Alexei, can you please not write to the towards the right edge of the board, because we cannot really see.
Oh, that's a boundary.
Where is the boundary exactly?
There was a line. Let's see where anyone is behind you. Right there. Yeah.
Sorry, sorry, I didn't realize that. Okay, let me write it in the right place.
Take my white also.
And for example, we can think of sigma z applied to spin number L, which is identity, then the sigma z, then the identity, and this is place L, the Lth place. And in this notation, the Hamiltonian is minus h. This is the transverse field. It's transverse to some other axis, sum over L. Sigma jz minus j sigma x L O L L plus 1. Is the Hamiltonian, and we would like to understand its ground states and some excited states for different values of h and j. And let's start with this simple example. H is positive and j is 0. And j is 0.
There's no periodicity of on the chain.
No periodic boundary condition yet. At some point, I'll try introducing a periodic boundary condition for simplicity, but the actual problem is just that. And in this case, we can define the ground state, and let me call it psi empty set, psi 0. Which is all speeds up. The second term is absent, and we basically have minus h times sigma z acting on each spin. And one can use a basis. Spin up is the same as 0, and spin down is the same as 1. And we can also use spin pointing to the right, which is up plus down over the square root of 2, and spin pointing to the left, which is up minus down over the square root of 2. This is the ground state. And one can consider excited states. For example, we can flip one spin, and that will be psi sub j. Of course, we can flip an arbitrary set of spins, and they will all be eigenstates of that Hamiltonian.
Can someone ask how the Pauli matrices act on the arrows? Or how do the Pauli matrices act on the arrows?
Sorry, I can't hear you. Can you speak up?
How do the Pauli matrices act on up and down?
The Pauli matrices act on up and down. This is in the basis of up and down. The first row corresponds to up, which is the same as 0. And the second row corresponds to down, which is 1.
Thank you.
The columns are indexed in the same way. And the excited state is spin number J is flipped. And this is a pretty boring story. It has no dynamics. We just flip a spin and it doesn't move anywhere. But now we can introduce a perturbation. We can turn non-zero J, but a small J. Before we do that, let's write the energies. The energy of this is not important. One can calculate that, but what is important is that flipping a spin has a particular energy cost, namely 2h. Now, suppose that h is non-zero and j is much less than h. And then we can write the Hamiltonian in the form h is h naught plus v, where h naught is the first term, it's large, and v is the second term, it's small. And perturbation is just minus sum over L and we can apply a general formula of perturbation theory that a perturbed eigenstate can be obtained this way. We start with the original eigenstate and add this sum of terms. A and B are indices of eigenstates, and we have there are quadratic corrections. So if we apply this result, we can find that the ground state will be perturbed, and the ground state will have so the perturbation flips two spins with indices L and L plus 1. So the contribution of such terms is small when J is small. This is a next order effect compared to the effect on excited states. Excited states changed drastically because previously all the states were eigenstates with the same eigenvalue, with the same energy. Now they won't be eigenstates. And we can write an effective Hamiltonian, which is a quasi-particle Hamiltonian. A flipped spin is somewhat like a particle. It's called a quasi-particle. And the quasi-particle Hamiltonian is 2h because that comes from the previous analysis, minus j of course, I should give a definition of the quasi-particle Hamiltonian. The quasi-particle Hamiltonian is meant to describe the following. Like the original Hamiltonian acting on this state, and we subtract the ground state energy. We count energy from the ground state energy. And such states form a closed subspace under the action of the original Hamiltonian. At least it's closed up to OV squared. And with this definition, we can write H from the previous analysis. And we should add two other terms because when we apply the perturbation, that is part of the Hamiltonian H, spins will flip. And in particular, if we start with the state psi sub j, which has one spin flipped, we apply the perturbation acting on these two spins, and the flipped spin moves to the left. And if we apply the perturbation acting on that two spins, if we apply the term like L sigma x sub L sigma L plus 1 x, then this spin will be up, and the spin to the right of it will be down. So there are other terms, plus j j minus 1. Actually, it comes with the minus sign. And it is this equation that is represented by the matrix. And of course, one can calculate the eigenvalues of that matrix exactly. Let me cheat a little bit, and then I'll make a correction. First, for simplicity, I put a 1 here and a 1 there, meaning that the chain is periodically closed. And then the eigenvalues of this Hamiltonian are calculated very easily because we know the eigenvectors. The eigenvectors are so And then we can act by this matrix on such an eigenvector. It's basically a column with these coefficients like e to the iq, e to the 2iq, so on.
In your formula of xi there, right? One of the b's in the bracket is be a.
Yeah, thank you.
That formula is if EB is for one thing, when they're all confident, all the one of things E minus EB minus EA equal to 0. I'm just not confused.
We assume that it's never zero. It's some non-degeneracy condition.
Okay, because I maybe misunderstanding the notation, because like over there, EH minus EMT is 2H, so all the EJs are the same, but over there, the EE minus EA.
Yeah, but I'm applying. Yeah, this is correct, and let me be more specific. We consider psi empty, and then empty J empty. Oh, it's L. Somehow I changed the notation from my notes.
And is the psi 0 the same as the size, or there's the
Yeah. Now it's the same as psi,
okay.
because the previous formula was general. It's and now it's specific.
Amazing. Thank you.
Sure. These are the eigenvectors, and the eigenvalues is 2h minus j times 2j times cosine q. And we can call it epsilon of q, but q here cannot take on arbitrary values. Q should be 2i k, some integer over n for a periodic chain. But in this equation, we can use an arbitrary q, and we can plot this this function. This is q. It's defined modulo 2 pi, but let it be from minus pi to pi. And this is epsilon of q. And it's called the quasi-particle energy. That is a function of momentum. In physics, such a function has other associated quantities, in particular the group velocity. A wave packet, a superposition of nearby quasi-particle states forms a packet that moves with velocity v equals the derivative of quasi-particle energy over the momentum. And means that in the presence of perturbation, in the presence of the second term, quasi-particles move with this velocity, and life becomes interesting. Now, was one case. Another special case is A is positive and H is 0. And in this case, there are two ground states.
Alexei, I have
Yeah.
a question. You modify the boundary multiplying by a phase, or you identify phase with the other. That now you get a one parameter family.
Yeah,
Circle.
yeah,
You still have an analysis like this that you can do.
yeah, yeah. This quantization condition will shift. So instead of this, there will be chi minus phi, something like that.
The spectral flow.
Yeah, yeah. But let me do something different. Let me just cross out this thing that was added for simplicity. Then this will become sine of QL, and Q will be pi K over n plus 1. Rest of the analysis will be applicable. In this case, when J is greater than 0 and H is 0, we have ground states. Given by this formula, sigma x, suppose it weren't the product of two sigma x operators, but just one. Then it would orient the spins in the x direction, depending on the sign of the term. The sign can be negative or positive, and in the negative case, all the spins will point to the right. In the positive case, they will point to the left. And each configuration is kind of self-enforcing because it's the product of two spins. And one can check formally that this will be eigenstates of the Hamiltonian and actually ground states. And quasi-particles also exist, but now they are interpreted as domain walls. And for example, we can have the spins pointing to the right, and starting from some point, the direction will change. And those domain walls will move if we make H non-zero. And each of these states will have some admixture of domain walls, like in the previous case, like in this equation. But something new can happen. A domain wall can start from the left and flip one spin, moving to the right, and it can flip multiple spins, and eventually it will flip all the spins, and the orientation will change. So if we start with this state, we can obtain that state, and eventually we can obtain the first state. And that's a virtual process, I'll using physics terms, there is a tunneling process in which a domain wall tunnels from the left hand to the right hand, and the tunneling induces a spin flip. And it means that the ground states in the presence of perturbations are no longer actually eigenstates. These two particular states are not eigenstates. They will be mixed. And the actual eigenstates will be the positive linear combination and the negative linear combination, like in this formula, with a plus and with a minus. And the tunneling amplitude will determine the difference between the two energies, and that energy is exponentially small in the length of the chain. And that can be obtained from the usual quantum mechanics analysis in this limit, when h is much less than j. However, this particular Hamiltonian has an exact solution. Everything can be calculated exactly. And that solution is pure luck, I would say. It happens in 1D systems. It rarely happens in 2D systems. And I don't know if it ever happens in high dimensions, that a model can be solved exactly. So in most cases, physicists do this kind of perturbative analysis and use other approximations.
Can I ask a stupid question?
Yeah.
I missed your meaning of the terminology quasi-particle. What do you mean by that?
Quasi-particle is something that behaves like a particle. A particle can be in some place and it can move. And that's what I meant. Oh, be erasing this. Okay. This is a Hamiltonian. There is a trick called Jordan-Wigner transformation. And
Like the
one writes sigma J and so on in terms of fermionic operators. But let me write it the other way around. Let me define operators C 2L minus 1. And I'll illustrate it by a picture. Instead of a spin pointing up or down, I'll use this kind of picture. Two dots inside the rectangle, two other dots, and those dots will be called Majorana modes, Majorana operators, and it's C1, C2, And in a general box, it will be C2L minus 1, comma C2L. And this is box number L, and that is box number 1. And I'll use such pictures to communicate faster than writing. This operator have remarkable commutation relations. Let me first begin with a general property. C sub j, either this or that, is Hermitian. And C sub j squared equals 1. If we square this operator, it's 1 because each of the Pauli matrices squared is 1. And operators with different indices anti-commute. This is for j not equal to k, but both equations can be written as part of one general equation. And you may recognize this is a definition of a Clifford algebra. The Majorana operators are just generators of the Clifford algebra. And which is the Clifford of some vector space, tensor C, and M is the real space of dimension 2n. And I wrote it in such a funny way because the commutation relations themselves just say that it is a complex Clifford algebra, and operators can be multiplied by complex numbers. However, this relation says that real structure is important, and that's why I'm using a real vector space. And since it's a Clifford algebra, we can talk about a vector space with an inner product. It's just the standard inner product, and we can define operators C of F for any vector in that space as sum over L, F sub L times C sub L. Or maybe I should say J from 1 to 2n, F sub J, C to that this commutation relation becomes C of F times C of F prime plus C of F prime C of F equals 2 times the inner product between F and F prime. And these are real vectors. So this is a Clifford algebra, and that is a representation of that algebra on a Hilbert space of dimension 2 to the n. And the representation depends on the choice of a basis. But if we choose a different basis, there is a canonical isomorphism of such representations defined up to sign. And I'll explain why that is the case. it has to do with the action of orthogonal groups on the corresponding Hilbert space. So first, before I erase this Hamiltonian, I should rewrite it in a new notation, and that will be the Majorana chain Hamiltonian. And the same Hamiltonian written in terms of the C operators, the Majorana operators. Uh, 2L minus 1 L. And this should be well, I and the idea is that the first two Majorana modes are coupled with strengths H. Actually, depending on how we define it, it could be 2H. You'll see why I put 2 here. And these two Majorana modes are coupled with strengths 2J and also coupled with strengths 2H and so on. Is a graphic representation of that Hamiltonian. And that is a special case of a quadratic Hamiltonian. Now, let me erase this and work with the Majorana chain Hamiltonian. I should warn you that the transformation between the two is non-local, and therefore some locality properties will be violated. And that's why it's better be called by a different name. So, general quadratic Hamiltonian H depends on a real antisymmetric matrix A. And it's defined like this. It's I over 4 sum for J and K, AJK, JCK. And if we use this definition, we get that the Majorana chain matrix two times this. Quadratic Hamiltonians, in terms of Majorana operators, can be solved exactly, and that's the trick. And in the remaining 5 minutes, I'll just some general properties of such quadratic Hamiltonians. Unfortunately, solution has to be postponed. But such operators form a representation of the group of the Lie algebra SO2N. So the map of A, which is an element of SO2N, real antisymmetric matrices from the Lie algebra. So is mapped to minus I H of A. And that is a representation. And it is a representation because of this formula. The commutation between minus IH of A minus IH of B equals minus IH A comma B. And the factor I over 2 is such that this formula actually holds. So we have a representation of this Lie algebra, and it extends to a representation of the Lie group, but it becomes projective. It is defined up to sign. And if we don't care about signs, it extends even to the full orthogonal group of 2n. We don't care about phase factors at all. So it's a projective representation of the orthogonal group. And using this projective representation, one can map representations of the Clifford algebra for different bases. But this will be an up to phase map. Now, let me define some objects associated with these representations. And the first type of object is an annihilation operator. L is C2L minus 1 plus I times C2L divided by 2. This is a discrete set of operators, but we can consider arbitrary linear combinations of such operators. And arbitrary linear combinations are given by C of F that map from real vectors to Clifford algebra elements for F satisfying this equation, and B is this particular matrix. And B squares 2 minus 1, it may be called a spin structure or complex structure. So these are annihilation operators. Another important object is vacuum vector. Remember that 0 means spin up and 1 means spin down. So the vacuum is when all the spins are up. And the vacuum vector can be defined in terms of the annihilation operators. So it is defined up to phase by the complex structure. And given a quadratic Hamiltonian, we can define a new complex structure and a new vacuum vector like this. If we have a Hamiltonian, this form, we can transform the matrix A into a special matrix Q this is positive times Q, Q transposed, and Q is an orthogonal metric. That's linear algebra. And epsilons are actually eigenvalues of A up to some factor. And using this matrix Q, we can define a new complex structure like B tilde equal to Q B Q transposed. The other way around, and this B tilde is I, the sign of the Hermitian operator minus I. And we can define a new set of annihilation operators and a new set of creation operators, they're complex conjugates, and a new vacuum. So in particular, one can define a new vacuum like condition that A tilde L annihilates that vacuum, and tilde L equals it's 1 over the square root of 2 C of UL, and this is UL is an eigenvector of matrix A. Eigenvectors of A are complex, and here we're applying this Clifford algebra map to a complex vector, and we're getting a complex operator, and such operators are related to the new complex structure. And this psi tilde is actually the ground state of the Hamiltonian H of A. So this is the general solution. Yeah, thank you for your attention.